Welcome to the lecture on number theory. This lecture is mainly designed for students who have completed their postgraduate studies in mathematics and are preparing for the competitive exams such as PhD entrance in mathematics or SET or state level eligibility test or NET or JRF or similarly GATE. So we will focus on applying the conclusions of the theorems and the results of number theory to the numerical exercises rather than delving into the detailed proofs. So we begin with the division algorithm in this lecture because that I believe is the first main step that one must know for going into any such entrance test. So this is division algorithm. We begin with division algorithm. So the division algorithm is defined in this way: given integers a and b in the set of integers with the condition that b is not equal to 0. Some authors also write b is greater than 0, but we can take b negative also, but it has to be non-zero, so actually we will choose it as a divisor. Given integers a, b belonging to z, there exist unique integers q and r. There exist unique integers q and r in z such that a is equal to bq plus r, where this r has the condition it is always greater than or equal to 0 but less than modulus of b. So this is division algorithm for any two integers a, b and z with b non-zero. We can find unique integers q and r, where we mainly call this q as the quotient and this r is known as the remainder. So once division algorithm is done, we will directly go to the fundamental theorem of arithmetic. So now we take up on the fundamental theorem of arithmetic, which states that if n is any positive integer, that means n is a number in the set of natural numbers, then we can express n as n equal to p1 power alpha 1, p2 power alpha 2, so on, pk power alpha k, where pi's are in fact distinct primes and alpha i's, they are also natural numbers. So this is the fundamental theorem of arithmetic. We can always express a positive integer n as a product of prime powers, and this factorization is sometimes also known as the canonical form of n. So this is our fundamental theorem of arithmetic. Now let's come to define the GCD and the LCM. GCD, which we also known as the HCF and read as greatest common divisor or highest common factor. This is defined as if a and b belong to z with a square plus b square not equal to 0. We use this condition to actually mention that both of a and b are not 0. At least one of them has to be non-zero to define the GCD. Then GCD of a and b is denoted by, we either write GCD of a comma b, or we simply write a comma b in this bracket, defined as d belonging to the set of natural numbers such that the first condition is d should divide a and d divides b. Second is, if there is another such positive integer c, if c divides a and c divides b, then c must also divide d. The first condition gives that d is a common divisor of both a and b, and second condition proves that d is the largest of all the common divisors of a and b. So this is the GCD, and now let's define the LCM. LCM, which we read as least common multiple. This is similarly defined as if a and b belong to z such that a is not equal to 0, b is not equal to 0. So here we have a condition that both a and b must be non-zero. It's only then we can define the LCM. Then LCM, which is denoted in this way, LCM of a comma b, or simply denoted this a comma b in the long intervals and defined as, then LCM is equal to D, or we can write L, such that the first condition is A must divide L and B must also divide L. So now here, since A should divide L and B should divide L, here we are forced to require the condition that A must be non-zero, B must be non-zero. If any of A or B is 0, then A divides L, B divides L will not be true. That will give an undefined equation. The second condition is if A divides some M and B also divides some M, then as we need this L to be the least common multiple, then L must also divide M. So first condition gives us that L is the common multiple of both A and B, and second condition makes this L to be the smallest of all the common multiples of A and B, so that it is the least common multiple. Now here we will use the fundamental theorem of arithmetic to find the LCM and the GCD. Now let's write it in this way. Given A is equal to, let's write its prime factorization, P1 power alpha 1, P2 power alpha 2, Pk power alpha k, and B is equal to Q1 power beta 1, Q2 power beta 2, Qs power beta s. Then GCD of A comma B. Now how do we define the GCD? We first pick up the common primes. So assuming that the common primes are R1, R2, so on, RT. So first we have to pick up the common primes between A and B. So these Ri's may be some Pi's, or they can be also some Qi's, but we just have to pick up only the common primes. That's the prime which appears both in A as well as in B. Now we have this common prime, suppose denoted by R1. It is appearing in A as well as in B. So R1 will have some power alpha I in A, and it will have some power beta j in B. Now among those alpha i's and beta j's, we have to pick up the smaller one. Let's call that smaller one as gamma 1. So first pick up a common prime and then choose its smaller power appearing in A and B. Similarly, R2 is another common prime. So assuming that its smaller power among A and B is gamma 2, and for RT it is gamma t. Then this product will be the GCD. And similarly, LCM of A and B. Now for LCM, we don't have to just pick up the common primes, but we have to pick up all the prime numbers appearing in A and B. If some prime number is appearing twice, that is A as well as it is appearing in B, then we have to pick it only once. So we pick up all the prime numbers. Let's call them as, say, Z1, Z2, so on, ZL. So let Z1, Z2, ZL be the list of all prime numbers that appear in A or B. Now, if Z1 appears in both of them, then we have to pick the larger power. Or if Zi appears only in one A or B, then we have to pick up that power. So let's call these powers as delta 1, delta 2, delta L. So this is the product that gives us the LCM of two numbers A and B. Let's pick up this theorem regarding GCD of two numbers. If D is equal to GCD of A comma B, then there exist integers x and y such that D is equal to ax plus by. Moreover, this set, which we shall denote by T, which is defined as like this ax plus by, where a and b are two given integers, and we list the set of all linear combinations ax plus by such that x comma y belong to z. This set is precisely the set of multiples of D, which is actually the GCD of A comma B. So therefore, the list of all linear combinations of A and B that forms a set T, which is actually the multiples of D. Now let's include one more theorem here, Euclid's lemma. This states that if a is an integer that divides the product b into c, and if a and b are relatively prime, then a divides c. Now let's take up the Euclidean algorithm for finding the GCD. So this is Euclidean algorithm for finding GCD. Here we will remember one main result. It is like this: if a is equal to bq plus r with the conditions of division algorithm, so we have 0 less or equal to r less than modulus of b. A and b are integers, b not equal to 0. Then we have this result GCD of a comma b. This is same as GCD of b comma r. Now using this conclusion we can find the GCD, as well as then reversing that process we can find the integers x and y with that linear combination. So now here we take up an exercise. So now in the solution, so what we do, we first of all write 46 and we divide it by 10. So we have 10 into 4, that is 40. 40 plus 6 is 46. So 6 is the remainder. Now we divide this 10 by 6. Now GCD of 40 and 10 will be same as GCD of 10 and 6. So we divide next, in the next step we divide 10 by 6. So it is 6 into 1 plus 4. Now here GCD of 10 and 6 will be same as GCD of 6 and 4. So we divide 6 by 4 and we get 4 into 1 plus 2. Now GCD of 6 and 4 will be same as GCD of 4 and 2. So we write 4 is equal to divided by 2, 2 into 2 plus 0. Now at this step we have to stop. The step where we get the remainder 0, then the remainder before that 0 remainder is the GCD. So therefore this is our GCD. Now GCD is equal to 2. Now reversing this process, now starting from this 2, we get 2 is equal to 6 minus 4 into 1. Now this is equal, now in the previous step we have this value for 4. So we get minus 6 minus, now for 4 we can write 10 minus 6 into 1. Now multiply it by 1. Now let's make some calculations. This is 6 into 1 here plus 6 into 1 here. So finally this is 6 into 2 minus 10 into 1. Now in the previous step we have the value for 6. The 6 can be written as 46 minus 10 into 4. Now multiply it by 2 minus 10 into 1. Now again make such calculations. This is 46 into 2 first of all. 46 into 2 minus 10 into 8 minus 10 into 1. So this is minus 10 into 9. Now finally we can write this like this is equal to 46 into 2 then plus 10 into minus 9. So therefore this is the value for x and this is the value for y. So that is the linear combination of GCD of 46 and 10 expressed as a linear combination of these two numbers. So this is the exercise for practice. Express GCD of 56, 72 as 56x plus 72y. Now let's come to the next topic, that is linear Diophantine equations. This equation ax plus by equal to c has a solution if and only if GCD of a comma b, which suppose we call as d, this must divide c. And in this case, if x naught, y naught is one pair of solution, then all solutions are given by x equal to x naught plus b by d into t, and y is equal to y naught minus a by d into t, where t is any integer. And here we have defined this d is the GCD of a comma b. Or we can also express the solution in this way, or we can write x is equal to x naught minus b by d into t. Then here we will write y equal to y naught plus a by d into t. Again we have the same condition, t belongs to the set of integers. So actually we have to write plus in one expression and minus in the other expression, and it is our choice where we will choose this minus. And how do we find this beginning solution or the initial solution x naught y naught? We will take up that exercise later on. Now let's define the prime numbers. An integer which is denoted usually by p, it must be greater than 1, is called prime if its only positive divisors are 1 and p. Now theorem regarding the prime numbers: if p is a prime and p divides a into b, then either p divides a or p divides b. If p is composite, or we can write if n is composite, then we may have n divides ab implies n divides a or n divides b. This can be the case, or we can have n divides ab implies n does not divide a and n does not divide b. So anything can happen. We can take the examples of both of these cases. Now let's write here. We can suppose write like 4 divides 12, then 4 divides 4 into 3. So here 4 divides 4, 4 does not divide 3. So we have one condition that 4 divides 4, but we can have the situation like this here: 4 divides 12. Then we can write 4 divides 6 into 2. Now 4 does not divide 6 and 4 does not divide 2. So this is the main thing that we want to note here. So this actually is not true for composite numbers, that if p divides ab, then either p divides a or p divides b. Now Euclid's lemma for the prime numbers, Euclid states that there are infinitely many primes. And here we have a very wonderful proof here that was in fact given by the Euclid himself. Suppose there are only k prime numbers or finite number of prime numbers. Suppose this is the list of k prime numbers. Then we define another number n is equal to p1, p2, so on, pk, the product of all these plus 1. Then either n is a distinct prime, or we can say this is a new prime which is different from these pi's defined, or n has a prime factor distinct from pi's. So that is how Euclid proves that there are infinitely many prime numbers. Now let's take up one more theorem regarding the primes. If Pn denotes the nth prime, then this nth prime is always less or equal to 2 power n minus 1. And this statement has the corollary, or this also concludes there are at least n plus 1 primes p which are less than 2 power n, because obviously the prime numbers p1, p2 up to p n plus 1, they will all be less than 2 power n. Using this theorem, the nth prime number is less or equal to 2 power n minus 1. Now here we mention just one name, that is Goldbach conjecture. This is Goldbach conjecture. We will not take the statement of the Goldbach conjecture, and it will be left as an exercise for you to find it yourself. So find the statement. Now let's write down another result that is given by Dirichlet. This is again regarding the primes. If a and p are relatively prime numbers, that is their GCD is 1, then the arithmetic progression contains infinitely many primes. This is the result given by Dirichlet. Now let's come to one nice topic, that is the congruences. For n belonging to n, for n in the set of natural numbers, a and b, which are also the integers, are congruent modulo n. We say these two integers are congruent modulo n if n divides a minus b, denoted by a is congruent to b modulo n. Now here we don't prove it, but this relation of congruence, this is a reflexive relation, this is a symmetric relation, as well as this is a transitive relation. So this is all these three. So this implies this is an equivalence relation. The relation of congruence is an equivalence relation, and the equivalence class is the partition of Z induced by this relation of congruence is denoted by. So this is the partition which is the set of sets. It is 0, 1, 2, so on up to n minus 1. So this is the list of all partitions. Actually the 0 now here, this denotes the set of all integers which leave the remainder 0 when divided by n. 1 denotes the list of all integers which leave the remainder 1 when divided by n, and so on. Now as we know that if we divide integers by n, there are n possible different remainders. So the list of all those remainders is mentioned in the Zn, which we call the set of integers modulo n results. We have if A is congruent to B modulo n and C is congruent to D modulo n, then A plus C is congruent to B plus D modulo n, and the most important result that we mention here is A into C. This is also congruent to B into D modulo n. This result is extremely important, and this is used so many times frequently in the exercises. And similarly, the second that we want to mention here is if A is congruent to B mod n, then this previous result implies K into A is congruent to K into B modulo n. That is trivial from this AC congruent to BD mod n, where we can say take the C and D both equal to K. But what we want to mention here is that if now KA is congruent to KB modulo n, then A is congruent to B modulo n divided by GCD of nk, n divided by GCD of n comma k. So that is important here. We cannot divide the congruences by k unless that k and n is relatively prime. And the third nice result that we want to mention here is that if A is congruent to B modulo n, then f of A is congruent to f of B modulo n for any polynomial f of x. So that is the property of the polynomials, that they preserve the congruences. Now let's come to the solution of the congruences. The congruence Ax congruent to B modulo n has a solution if and only if GCD of A comma n, which is equal to D, it should divide B now. So we have to pick up the GCD of A and n, it should divide this B. Also in this case, Ax congruent to B modulo n has exactly D solutions in Zn, which we can also read like this. And in this case, Ax congruent to B mod n has exactly D solutions modulo n, or D solution, D incongruent solutions. Moreover, the solutions, or we don't need to write these, we can write the solutions of Ax congruent to B modulo n form an arithmetic progression with common difference n by d, where n is the moduli and d is the GCD of A and B. We will take up this exercise, find all solutions of 12x congruent to 6 modulo 18. So here GCD of 12 and 18, that is equal to 6, and 6 divides 6. So there are 6 incongruent solutions. Now let's find these solutions. So what we are given 12x is congruent to 6 modulo 18. Now 12 and 18, they have GCD equal to 6. We will try to divide this GCD using this property that KA congruent KB mod N is congruent A comma A congruent B mod N divided by GCD of NK. So this implies, now dividing by 6, we get 2x is congruent to 1 modulo 18 divided by GCD of 6 comma 18. So this implies 2x is congruent to 1 modulo number 18 divided by 6, that is equal to 3. In comparison to 12x congruent 6 mod 18, this congruence is easier to handle. Now clearly, now actually we have to put the values from Z3 here. Z3 has the value 0, 1, 2. So we have only 3 choices to handle. Put 0, we do not get it as solution, but if we put x equal to 1, it is not a solution, but x equal to 2 is a solution, because 2 into 2 is 4, 4 minus 1 is 3. So clearly x equal to 2 is the solution. And in fact, this will be the smallest of all the solutions in Z18 for the given congruence. So this implies x equal to 2 is the solution of 12x is congruent to 6 modulo 18. Now how do we find the other solutions? Now as we know, the solutions of this congruence form an arithmetic progression with common difference n by d, and n by d here is equal to 18 divided by 6, which is equal to 3. Therefore the solutions are, the first solution is 2, next is equal to 2 plus 3, which is equal to 5, which is equal to 5. Next solution is equal to 5 plus 3, which is equal to 8. Next solution is equal to 8 plus 3, 11. Then 11 plus 3, 14. Then 14 plus 3 equal to 17. Now 17 plus 3 will be bigger than 18. So we conclude the solutions are 2, 5, 8, 11, 14 and 17. So therefore we have found the 6 solutions of this congruence. Now let's come to the very important topic, that is the Chinese remainder theorem. So what Chinese remainder theorem states? Given the congruences x congruent to a1 mod m1, x congruent to a2 mod m2, so on, is congruent to an mod mn, have a common solution where mi's are pairwise relatively prime, have a common solution given by, the solution is denoted by x, which is defined as a1 m1 inverse mod m1 plus a2 m2 inverse mod m2, then plus so on, plus finally plus an mn inverse mod mn, now whole modulo m. So they have a unique solution modulo m, where capital M is defined as the product of moduli mn and this capital Mi. This is defined as m divided by mi, which can be read as the product of moduli divided by. So this is how do we define the solution using the Chinese remainder theorem. Now we take this exercise, find the common solution of x congruent to 1 mod 2, x congruent to 2 mod 3, x congruent to 3 mod 5. Or the same exercise can be asked like this: find the positive integer which leaves the remainder 1 when divided by 2, which leaves the remainder 2 when divided by 3, and leaves the remainder 3 when divided by 5. So the solution is x equal to a1 m1 inverse mod m1, we have 3 moduli here, plus a2 m2 inverse mod m2 plus a3 m3 inverse mod m3, now whole mod m. Now let's see what are these values of mi's and m. Now m is the product of moduli 2 into 3 into 5, which is equal to 30. m1 is this 30 divided by 2, that is 15. m2 is 30 by 3, that is 10. m3, that is 30 by 5, that is 6. And similarly, a1 is 1, a2 is 2, a3 is equal to 3. So thus our x is equal to, now a1 is 1 and m1 is 15. Now we have to find the 15 inverse mod small m1, that is 2. Then plus second a2 is 2 into 10. Now we have to find 10 inverse mod 3. Then plus 3 into 6 inverse mod 5. Now we need to compute these three values: 15 inverse mod 2, 10 inverse mod 3 and 6 inverse mod 5. Now by inverse we mean now 15x is congruent to 1 modulo 2. Solving this congruence will give us the inverse of 15 modulo 2. But this gives, now first we divide this 15 by 2, it will leave the remainder 1, so this gives x is congruent to 1 modulo 2. That's itself a solution. This implies 15 inverse is just equal to 1. And our second is 10 inverse. For 10 inverse we solve the congruence, 10x congruent to 1 mod 3. Now dividing this 10 by 3, we get the remainder 1, so this gives x is congruent to 1 mod 3. So this implies 10 inverse is equal to 1. So these congruences are easier to handle. Now next one we have 6x is congruent to 1 mod 5. Now again dividing 6 by 5, we get the remainder 1, so this gives x is congruent to 1 modulo 5. So this implies the 6 inverse, this is also equal to 1. We will not get so easily every wire in every question, but here we got them easily. So this implies x is equal to, now 1 into 15, that is 15, into 15 inverse, that is 1. Now 2 into 10 is 20, into 1, that is again 20, and 3 into 6 into 1, that is equal to 18. We have computed this whole as modulo 30. Now this is congruent to, now 15 plus 20, that is 35, then plus 18 modulo 30. Now we can apply the modulo 30 on this 35, it will leave the remainder 5, then plus 18 modulo 30, and finally this congruent 18 plus 5, that is 23 modulo 30. So therefore this 23 is the solution. So now let's try if this 23 really satisfies all the polynomials. Now 23 minus 1 is 22, it is divisible by 2. 23 minus 2 is 21, it is divisible by 3. And 23 minus 3 is 20, it is divisible by 5. So that is the correct solution. Now we move to the new dimensions of Chinese remainder theorem, or the different dimensions of Chinese remainder theorem. And the case is when moduli are not relatively prime. Here first we mention one theorem. The congruences x congruent to a1 mod say k1 a2 x congruent to a2 mod k2 so on x congruent to an mod kn, where ki, kj is not necessarily equal to 1. Now sometimes it may be 1 and sometimes it may not be 1. Have a solution if and only if GCD of ki, comma kj, suppose this is equal to d, this should then divide ai minus aj for all I not equal to j. Now what we have to do here, we have to check it pairwise. Whenever we choose ki and kj, it is GCD should divide. The same remainder difference is ai minus aj. So ki will be associated with ai, kj associated with aj. Then GCD of ki kj should divide ai minus aj. Now if the GCD of ki and kj is equal to 1, then it will always divide ai minus aj. So therefore we only need to check it the case where GCD of ki and kj is not equal to 1. Now let's take up an exercise and see how do we apply these. Now let's take up this exercise. Find the solution of x congruent to 7 mod 9, x congruent to 13 mod 15, x congruent to 4 mod 21. Now let's find the solution of this kind of a congruence where the moduli are 9, 15 and 20. Now obviously they are not relatively prime. Okay, in the solution what we do, we will directly start with the solution. X is congruent to 7 mod. We will write this 9 as the prime factorization 3 into 3. The second congruence is x congruent to 13 mod. Now write 15 as 3 into 5, x congruent to 4 modulo. Write 21 as 7 into 3. Now these congruences can be written as like this. X is congruent to, we will split the congruences to the number of prime factors involved in moduli. So x congruent to 7 mod 3, and similarly this will give us x is congruent to 7 mod 3. This will give us two congruences which are in fact similar. Now second one, x congruent to 13 mod 3, and second one is x congruent to 13 mod 5. Now here x congruent to 4 mod, we can write 3 in the beginning. Now x congruent to 4 mod 7. Now let's simplify these congruences. So they give, now dividing this 7 by 3, it leaves the remainder 1. So we get x congruent to 1 mod 3. Now similarly here x congruent to 1 mod 3. Now x congruent to, now divide this 13 by 3, again we get 1 mod 3. Now here we get x is congruent to 3 mod 5. And here we get x is congruent, again 1 mod 3. Here we get x is congruent to 4 mod 7. So now we have to pick up only the distinct congruences. Like we have the first congruence, x congruent to 1 mod 3 repeated 4 times. Now here we have the distinct congruence, and here we have the distinct congruence. Now looking at these three congruences, we have the moduli as 3, 5 and 7, which are now relatively prime. Now we can apply the Chinese remainder theorem. So therefore now apply Chinese remainder theorem. So this is one dimension of the Chinese remainder theorem when the moduli are not relatively prime. Another dimension we can take here is another case when we have congruences like this solo. Suppose 2x congruent to 3 modulo 5, 3x congruent to 4 mod 7, now 2x congruent to 8 mod 10. So this is actually a mixed case. First of all, we don't have x congruent to a mod m, we have 2x congruent to 3 mod 5. Now here similarly 3x here and here 2x. But now there is one more different situation here. 5 and 10 are not relatively prime. 7 and 10 are relatively prime. 5 and 7 are relatively prime, but 5 and 10 are not relatively prime. Now how to handle these congruences? We have to do it like this. In the solution, the first congruence is this 2. This 2 is relatively prime with 5. So now this 2 will have the inverse in Z5. So therefore we can write the first congruence, multiply both sides by. So we multiply the first congruences both sides by 2 inverse. Now this gives 2x is congruent to 2 inverse into 3 mod 5. So that is first one. Now 3 has inverse in Z7, so we multiply by inverse. This gives x is congruent to 3 inverse into 4 modulo 7. Now third one is we cannot multiply with the inverse, but we can in fact divide by 2 the congruence throughout. So we divide by 2. Third congruence, q is x is congruent to 4 modulo. Now 10 by 2, that is 5. Now solving these congruences, now these congruences give, now 2 inverse is equal to 3. So this gives x is congruent to 9 modulo 5. 3 inverse is equal to 5. So this gives x is congruent to 20 modulo 7. Now here x is congruent to 4 modulo 5. So now they give, now dividing this 9 by 5, we get x is congruent to 4 modulo 5. X is congruent, dividing this 20 by 7, we get 6 modulo 7. And now the third congruence is repeated. So we have these 2 congruences instead of the given 4 congruences. Now these congruences can be solved by Chinese remainder theorem because 5 and 7 are relatively prime. So therefore apply Chinese remainder theorem now. Now let's move to the another heading. So this is the theorem like this. The system of congruences. The system of congruences ax plus by congruent to r mod n cx plus dy congruent to s modulo n have a unique solution if GCD of AD minus BC and n is equal to 1. Otherwise it has no solution. Otherwise is not a case here. So this is just this kind of statement. If this is equal to 1, then it has a unique solution. If this is not equal to 1, then sometimes it may have a solution and sometimes it may not have a solution. We will not take up that condition here. Now let's come to define the Fermat's theorem. Let A belong to the set of integers and P be prime, then the first case is A power P is congruent to A modulo P. This condition is always true, or this equation or congruence is always true. And the second congruence is A power P minus 1 is congruent to 1 modulo P. But here we have a condition if A and P are relatively prime. Otherwise this is not true. Now this has an implication of Fermat's theorem. A plus 1 power P, this is always congruent to A plus 1 modulo P. Now here we take an exercise. Find 5 power 38 modulo 11. Find 5 power 38 modulo 11. So let's try to find out a solution using the Fermat's theorem. So we have 5 power 11 minus 1 is congruent to 1 modulo 11 using the Fermat's theorem because 5 and 11 are relatively prime. So this implies 5 power 10 congruent to 1 modulo 11. This implies 5 power 30 raising the power 3 on both sides is congruent to 1 modulo 11. So we have reached 30, but now we need 38. For that thing, what we do, we start from the beginning. 5 is congruent to 5 mod 11. This is always true because relation is an equivalence relation. Now 5 square is 25 and 25 is congruent to 3 mod 11. Now 5 into 3, 5 cube, that is 5 into 3, 15. So 15 is congruent to 11 mod 4 mod 11. Now similarly 5 power 4. Now multiply this equation by 5, we get 20. 20 is congruent to 9 mod 11. Now 5 power 5. Now multiply this both sides by 5. 5 into 9 is 45 and 45 is congruent to 1 modulo 11. So therefore we can multiply this congruence and we can multiply this congruence. Now multiplying these congruences, we get 5 power 35 is congruent to 1 modulo 11. Now we already have 5 power 3 here. Now multiply these two. we get 5 power 38 is congruent to 4 modulo 11. That is 5 power 38 modulo 11. This is equal to 4. So that is 4 is the remainder when 5 power 38 is divided by 11. Now let's take up another theorem that is similar to the Fermat's theorem. If a power p is congruent to a mod q and a power q is congruent to a mod p, then a power pq is congruent to a mod pq. And similarly, the second statement similar to this one is p power q minus 1 plus q power p minus 1. This is always congruent to 1 modulo pq, where p and q are primes. Where p and q are primes. These both results have this p and q to be prime numbers. Now let's come to the Wilson's theorem. This Wilson's theorem states that p minus 1 factorial is always congruent to minus 1 modulo p for any prime p. Now how do we apply the Wilson's theorem? We will take up one exercise here. Okay, in the solution what we do, using Wilson's theorem, we have 29 minus 1 factorial is congruent to minus 1 mod 29, because 29 is a prime number. So this implies 28 factorial is congruent to minus 1 mod 29. This implies, now we have to reach 26, so we can write 28 into 27 into 26 factorial is congruent to minus 1 modulo 29. So this implies now 28 is congruent to minus 1 mod 29. So instead of 28 we can write minus 1, and instead of 27 we can write minus 2 into 26 factorial is congruent to minus 1 mod 29. Here we mention these things. 28 is congruent to minus 1 mod 29. 26 is congruent to, it is actually 27. 27 is congruent to minus 1 mod 29. So this implies, now multiplying minus 1 into 2, that is 2 into 26 factorial is congruent to minus 1 mod 29, but remainder has to be always positive. This implies 2 into 26 factorial is congruent to 28 mod 29. So therefore the remainder, when 2 into 26 factorial is divided by 29, the remainder is 2. The remainder is 28. Now second part, to show 18 factorial is congruent to minus 1 mod 437. So here what we do, we have 437. This is equal to 19 into 23. Then Wilson's theorem gives us that 19 minus 1 factorial, that is 18. By Wilson's theorem we have 18 factorial is congruent to minus 1 mod 19. So let's call this equation number 1. Now by Wilson's theorem again, we have 23 minus 1 factorial is congruent to minus 1 mod 23. Now 23 minus 1 means 22 factorial. So this is 22. Now let's count 18, 22, then into 21, then 20, then 19, then 18 factorial. This is congruent to minus 1 mod 23. Now 22, it is congruent to minus 1 mod 23. 21 is minus 2 mod 23. This is minus 3 mod 23, and this one is minus 4 mod 23. Then into 18 factorial, congruent to minus 1 mod 23. Now multiplying these numbers, we get 24 into 18 factorial is congruent to minus 1 mod 23. But 24 is congruent to 1 mod 23. So this implies 18 factorial is congruent to minus 1 mod 23. Now let's call this as equation number 2. So this is our equation number 2, and now 18 factorial is congruent to minus 1 mod 19 as well as 23. Now we can multiply these two congruences using the Chinese remainder theorem. So using Chinese remainder theorem, these two congruences have a, now since these two congruences have a common solution, so we can write these congruences as 18 factorial is congruent to minus 1 mod 19 into 23, that is 437. So that common solution will be also a solution of this congruence. Now let's take up another theorem, the quadratic congruence. The quadratic congruence x square is congruent to minus 1 modulo p has a solution if and only if either p equals 2 or p is congruent to 1 modulo 4. So this is again another result that we must remember. Now some number theoretic functions. We define them quickly like this. The first one is pi of n, which is defined as the cardinality of the set x belonging to Zn such that x and n are relatively prime. The order of this set is called phi n. And here we also want to mention that the set x belonging to Zn such that x and n are relatively prime, this set is denoted by un, which we also call the set of units of Zn, and this will be discussed in group theory in detail. Now second set that we want to define here is the number theoretic function tau n, which is defined as the number of divisors, in fact positive divisors of n. The third number theoretic function we want to take up here is sigma of n, which is equal to the sum of all positive divisors of n. And we also mentioned their formulas, so theorems regarding this thing. First of all, this phi of p power alpha, this is defined as p power alpha minus p power alpha minus 1, and second one is phi of mn, this is equal to phi of m into phi of n if m and n are relatively prime. So this property is known as the function is multiplicative. So this is first one. The second one is tau n, which is equal to tau of p1 power alpha 1, p2 power alpha 2, so on, pk power alpha k. So we must have a prime factorization of n. Then this tau n is equal to alpha 1 plus 1 into alpha 2 plus 1 into alpha k plus 1. That means we just have to take up the powers, add every power by 1 and multiply all the numbers. That gives us the number of divisors of n. Now the sum of divisors sigma n, which is equal to sigma of p1 power alpha 1, p2 power alpha 2, pk power alpha k. Now this is defined as p1 power alpha 1 plus 1, then minus 1 whole divided by p1 minus 1. Now multiply this by p2 power alpha 2 plus 1 minus 1 divided by p2 minus 1, then so on. Then similarly pk alpha k plus 1 minus 1 divided by pk minus 1. So this is the formula for phi n, tau n and sigma n. And we mention one more thing, pi n, tau n and sigma n are all multiplicative. These are all multiplicative functions. By multiplicative function we mean that like phi of mn is phi m into phi n. Similarly tau of mn is tau m into tau n, provided m and n are relatively prime. And similarly sigma mn is sigma m into sigma n if m and n are relatively prime. Now the final result that we want to take up regarding these number theoretic functions is summation d divides n 1 by d. This is equal to sigma n divided by n for every n belonging to the set of natural numbers. So this is all about the today's lecture. Now it is recommended that you take up some exercises from the books and also complete the exercises that I have left unsolved here to practice properly and remember all the things properly.